Predictive and preventive maintenance on the electric distribution grid is a best practice that increases reliability, reduces costs, and saves lives. John Laletta, founder of Exactor, explains how utilities use Exactor's patented process to improve their distribution system performance. Here is John's presentation.
Near and dear to my heart, and something that is not only an important part of operations of a utility, but has some real meaningful results that we'll go through in our presentation. So I can't see you today, but I imagine if I ask the question, who knows what a hat trick is, someone would raise their hand. And so I'll answer the question myself. It's when you get three things happening in one game that are important to your team. It might be three goals at a hockey game, for instance, by one person. And that hat trick is an important part of this scheme because there's not just one benefit from doing predictive maintenance on the grid. There are many. And we're going to look at that, see how they all hook together, see what they cost, see what the results of that are, look at a couple case studies, and then have an open time for some questions and answers at the end. I want to start by evaluating or presenting rather the real important question that I see as an issue in the electric utility world all the time, and that's how can we improve? There's always a need at a utility to reduce injuries, reduce costs, speed up response to outages, reduce outages, and so on. So usually what happens, in my experience as an electric utility engineer for many years before getting involved with Exactor, was someone comes to the operations group and says, what are you doing today? Because we got to get better. And the response typically is, well, we need more money. We need a bigger budget. We need more people. We need more resources. And the money flows in because the need for improvement exists. And what happens is we get more of what we're doing today, just more of it. And that's a way to improve, but it's not the best way to improve. A better way to improve is to look at what you could do if there was a different way to really make a difference in the utilities operation. So that's what we're going to talk about today, a different way to approach grid maintenance. At the power plants, if you have power plants in your company, you know that they do predictive maintenance continuously because they can't afford a piece of equipment to fail and maybe jeopardize generation. And and that's a little easier situation for the power plant because there's four walls and everything is contained in those walls. And you can go up and touch it, see it, and evaluate its operation, every pump, every switch, every breaker, and really get a feeling for when something needs help, maybe needs maintenance or needs replacement. But on the grid, it's a much different story. I mean, the distribution grid in the United States is the largest machine in the world. It's 4.5 million miles of interconnected operating system with billions of components that if any one of those components fail, a circuit or an area or a substation will fail. And all those people will have issues with their delivery of power. And it's not protected by four walls. It's open to the environment in every fashion: weather, wind, lightning, earthquakes, volcanoes, everything that can affect every one of us in our daily lives can affect the electric power grid. So it's a big job. There's no question about that. But we're going to talk a little bit about maybe how we can change the way we address our approach to grid maintenance, and specifically in this presentation, the distribution grid. Now, this is the DOE's estimate for the entire United States, a blended estimate of what the causes of electric outages are: trees, equipment, animals, and then the unknown. And the unknown is a big part of equipment failure because if a line crew goes out to restore power on a circuit that's out, and they look at it and they can't find the problem, there's no trees nearby touching it, there's no dead animals laying around. Uh, all they and there's no pole broken by a car accident. All they can do is say, I don't know what caused the outage, but when I slammed my fuse back in, the circuit held, and I'm going home now. So it's a issue of what is addressable and what is not addressable. And in the past, trees and animals were very addressable. You guys know how to do that in many ways. But equipment and the unknown part of your outages is virtually unaddressed, except when something fails, like a pole top transformer pops its lid and catches fire, or a disconnect operates, or the fuse blows and you have to replace that. Or if you see something like a broken cross arm or a cracked insulator or a loose conductor laying on the cross arm, those kind of things are the typical response to equipment failure. But we're going to get right down to what it is that has failed and how we can predict that it's going to fail and how we can then react to that prediction. Most utilities will tell you that they have a run to failure strategy when it comes to electric grid equipment. An outage occurs, resources are mustered, extraordinary effort is put out, and the circuit is brought back into compliance and operation. There's problems with that, though. You're allowing the piece of equipment to fail, the transformer to catch fire, the insulator that's cracked to flash over, whatever it is, you're allowing that to happen. And when it happens, then you have to react. Now, the goal of that, of course, is to maximize the use of the equipment until it actually does fail. So a lot of utilities will use this as the reason for run to failure. Let's get every inch and minute out of that equipment before we replace it. For non-critical equipment, that's okay. But really, is there a piece of equipment on the distribution grid that's non-critical? Because is there a piece of equipment that if it fails, you won't have an outage? Or if it fails, something worse could happen, like a lightning arrestor? If a lightning arrestor fails, the equipment it's protecting may get damaged at the next lightning strike in the area. So this presents us with a heightened risk and more unexpected failures. And there's just no way to get around that. The cost, though, can be confusing, because when you're only replacing things that have failed, you would look at the cost sheets and say, well, gee, we saved a lot of money by letting that run to failure. But did you? Because there's a number of elements that are affected by that failure that we're going to talk about here in a moment. But let's now look at the other side of this, and let's talk about predictive maintenance. And predictive maintenance has a meaning that's defined by its name. It means rather than waiting for a failure, we're going to predict that a failure could occur, and if the failure result would be important, we may want to do something about it before it occurs. Now, the difficult part of predictive maintenance is you have to know the condition of all the equipment that you have in your predictive maintenance program. Those billions of devices, it may be tens of thousands to a million in your company, all the insulators, all the cross-arm connections, all the lightning arrestors, disconnects, fuse cutouts, all that equipment has to be evaluated for its performance while it's running. So what we want to do in predictive maintenance is, rather than wait for the failure, we want to use the condition measurements of the equipment to let us predict it's probably going to fail, and soon. It's an incipient condition. that if it fails, we're going to lose this circuit, we're going to affect this hospital, we're going to have so many customers without power, and that's going to rack up our CMI and hurt our indices of SAIDI and SAFE, and we don't want that to happen. So when we can predict a failure, we can do something about it early. The benefits are reduced unexpected failures. We're always going to have unexpected failures, but we can reduce the amount of them and the intensity of the impact on the grid by taking these condition-based measurements and doing predictive maintenance. So the risk to the utility from an outage, and we'll define those risks here in a moment, are reduced because we're getting rid of some of them. And you have less unexpected failures, which gives you a better operating profile. Now, there are upfront costs for this. We have to measure the condition of this equipment. We have to know, is it in a state that is normal and as designed, or is it in a deteriorated state that could fail? And when the failure is imminent, the impact of that failure is going to be felt. But we're going to look at the costs as well as the benefits here in a moment. So how do you improve your performance as a utility by using predictive maintenance, and how do you get that predictive maintenance hat trick? Well, first of all, you find more efficient and effective ways to reach the goals of improved performance. Rather than just throwing money at the problem, let's put money into changing the approach that we take on supporting the grid and avoiding outages. We don't want more effort and more time and more expenses as a result of this. So we need to have a controlled environment that addresses the problem as well as is a more efficient way to go at it. We want to use strategic tools, not just manpower resources added on. We have the techniques that we can use that have been tried and true over decades at power plants and manufacturing and industrial plants by doing condition-based maintenance on equipment. We can maximize our productivity. When you're doing scheduled maintenance of, let's say, a lightning arrestor change during the daylight hours, during normal operating procedures, with a photograph of the piece of equipment that needs to be replaced, so you have exactly the knowledge you need when you get to the site and have all the equipment on your truck to do the job in a safe way, you're going to be safer, you're going to be more effective, and you're going to get the job done in a most efficient way. We're not going to add effort. So as we add effort to the work that we're doing, the effort could be measuring the condition of this equipment. Well, we don't want you to do that. We want to provide that measurement of equipment condition, that deteriorated equipment evaluation for you in a way that's very easy for you to use to schedule and complete work. And because we're doing work now during the day, during scheduled hours, during a period when the grid is energized, so we're not looking for the problem with multiple crews, but we're finding the problem based upon reports, we can go right to the problem, solve the problem in the most safe way for the workers that are involved. So what can you get from this? Well, this is aggregated data from our 18 years of history of running predictive maintenance programs in the United States and 5 other countries. The first thing is you can reduce the outage duration by up to 18%. What does that mean? That means your customers are going to have, if they experience an outage, a shorter period of outage. Why? Because you're going to know before you go out to seek the problem what could be the problem based upon the condition measurements that have already been taken. We're going to reduce crew costs by 33% because they're going to know what to do and when to do it for predicted deteriorated equipment. and get most of those out of the system. And then they're only responding to other devices that we already know the condition of. And they may have been a little less deteriorated when we took the last readings, but you know where they are. It's a good place to start your journey to restore power rather than just going out and saying, well, the circuit's done. You take your truck and go to the end. I'll go to the other end. We'll come and try to meet in the middle and see if we can't find something like a tree limb that's touched the wire. And because we're doing work during business hours, normally scheduled hours, during daylight, moving the work from a rainy day to a dry day, we can reduce the rate of injuries and fatalities by up to 38%. And to me, that's the real win. Keeping people safe in their work is certainly the joy that we have in bringing this to the marketplace. And it makes sense, right? The number one reason for trips and falls is darkness. So if you're working at night and injuries occur, it's because you can't see what you're doing. I mean, it makes sense, right? But during the day, when things are calm, things are scheduled, you have all the equipment on your truck you need, it's easier to get the job done safely. So how do you effectively create a predictive maintenance program? Well, we mentioned you have to know the condition of all the equipment on the grid. Now, we could put sensors on all the equipment on the grid, or we could have a sensor that's mobile that visits every pole on a periodic schedule and records and defines the deterioration of the equipment on that pole and gets right down to, on a combination unit, is it the lightning arrestor or is it the cutout itself? Is it the bushing on a transformer or is it the transformer? So getting right down to that rifle shot result can be done, and we'll show you how, using deployed mobile sensors that move from pole to pole and measure the condition of the electrical equipment. Now you'll know where the weaknesses are on your system. And it's up to you to decide, should I pull maintenance on this or not? If it's a overhead lamp at the end of a single phase feeder near an alleyway, maybe you don't want to change that out right away. But if it's a transformer that could take out 8 or 9 customers and cause a pole fire and maybe damage vehicles parked underneath it, you may want to get to that a little bit earlier. And the other thing that you can use this data as a strategic tool. So if you know that you have a weak area in your system, weak meaning more deteriorated equipment than other places, you can direct capital expenditures just to that area rather than kind of peanut buttering capital expenses across the grid saying we're going to improve reliability by doing projects everywhere. Get the money flowing to those projects that really require attention and can have an immediate and significant impact on the results of the work that's done. So what changes for you? Well, you received some things. You received reduced unexpected outages. That's a good thing. You have less chance of people getting injured, less chance of outages occurring without any forewarning. You get planned grid maintenance. So now you're doing things on your schedule, not on the grid schedule. And what do you avoid? Well, because we're talking about a mobile deployment of sensors, you avoid any additional equipment being added to the grid, which also affects grid reliability. You don't have to manually monitor any equipment for deterioration or a condition that would affect its operation. So what does Exactor provide in these programs? We collect all the data required for your predictive maintenance program. We install sensors on fleet vehicles, and we target a geography with you so that we know where best to deploy sensors Could be your whole grid, could be a section of the grid. And then our mobile sensors manage the collection of data about deteriorated equipment, location of that deteriorated equipment, and finally, identification of that deteriorated equipment. So you know exactly what's the problem at a pole. Is it a pin insulator that may flash over and cause that circuit outage? Or is with pin insulator with high leakage current that could cause a pole fire that's even more expensive? Or is it a lightning arrestor right next to a transformer that's no longer operating properly? One of our latest developments is an IoT sensor that goes on garbage trucks. And we have contracts with the national haulers of trash collection across the country. The sensor goes on the truck, and as the truck collects garbage, it's monitoring every pole that goes by and picking up deteriorated signals so that you can see that, gee, after that last big windstorm we had, there's a increase in deteriorated equipment in this area. So we better get some extra equipment out there and do some predictive maintenance right now because we see the problem is growing. We did a 2-year, 500,000 mile or so project with these sensors. And that was the opportunity for us to test our new sensor. It's something that we're very proud of. It goes well with the trash collection operations because there's no wiring, there's no power. It just glues onto the truck. Think of a big command strip. And now we can deploy these sensors anywhere we want. And in the development project, which was over a 2-year period, we knew we had to hit all these goals. And that made the sensor compliant with the needs of the trash collection people. And of course, they participate in the revenue that's produced by using these sensors in electric utility operational condition monitoring. The key thing here is that we use partial discharge VHF RF emissions. And it's not just noise, it's a very special signature that is produced when an incipient failure condition is presented. And in doing that, we now have been able to say that if we say there's a problem at this pole with this piece of equipment, 99%, better than 99%, of our findings are are found in the field as an effective problem that could be a near-term failure for the utility. So we're not just bringing information to you; we're bringing important information that will allow you to get the benefits of this program. The way our system works, this is just a graphic, but you can imagine the garbage truck running around, and as it's going by the poles, the emissions coming from the pole will present themselves to our sensor that picks that up, analyzes it in real time, and sends information to our servers so that we can then gather that information and evaluate the area. Now, there's a real benefit to using these RF emissions over things like thermal emissions, or some people use corona. Of course, you can't use that typically in distribution because there's no corona at lower voltages. But our technique is very scalable. One sensor on a garbage truck can look at 16,000 poles a week and gather information on up to 80,000 pieces of equipment, that each one of those pieces of equipment, if they fail, will cause an outage. Our system is not load dependent. It doesn't matter if there's any current flowing on the system. It just needs to be energized. We're not weather dependent. If the people can collect trash, we can measure our condition the way we do without any deterrence to the efficacy of the measurement we're making. And like I said, when we tell you something's wrong, 99+% of the time you're going to find the problem in the field. So that's a pretty good hit rate. And because RF emissions are very high frequency, they go right through homes, cars, and businesses. We don't have to go down alleyways. We don't have to go behind and back lot lines. We just drive down public thoroughfares, whether it's a directed drive with one of our vehicles or the garbage truck collection scheme. And this is what we find. We find more pin insulators than anything else. And guess what? You have more pin insulators than anything else. So it kind of makes sense. Then we get down to other types of insulators. Dead-end insulators specifically are a real problem with pole fires. Cutouts are the next, surge arresters, connectors, all the way down, even non-utility equipment. If a cable TV amplifier catches fire on your pole's involved in a pole fire. It doesn't matter, it's not your equipment. So we'll tell you about those, and you can work with your partner who's doing leasing of area on your pole to get it replaced. And this is what utility gets: a complete description of the location of the pole that has the problem, a satellite view of where that pole is. You might be in the area doing other work and want to pick this up as an adjunct job, and a high-res photograph of the piece of equipment that is in this incipient fault mode. It's going to fail. If you pull it out, it won't, and replace it. It won't fail. If you leave it in, it's going to fail. And that's really the proposition that we offer. The data comes to our customers in almost real time. You see exactly where the surveys ran, the black lines you can see on that chart. You get information about, excuse me, how many CMI or customer minutes of interruption will occur if this failure occurs. So you can make judgment calls and prioritize your work in doing it in a way that's most effective for you. We aggregate all the degraded signals, and we give you an exact prediction of what's going to fail and how it will affect your operating system. So this is just an example of one survey. The white lines are the survey where the vehicle ran itself. The red dots are all the detections of these VHF RF emissions that have the signature of deteriorated electrical equipment. A lot of noise there. There's a lot of transients there. A lot of conditions that are the same signal over and over again, just permeating down the line. So after we take the raw data from several passes of the grid, then we run it through our secondary process, which selects those key targets that you'll want to work on. And these are the blue dots. So that 1,100 number of readings turned into 77 important incipient failures that if you take care of, this grid will perform at a much higher performance level. When we do our work, we'll sit down with you and gather your reliability information, not SAIDI and SAIFI for all outages like vegetation and animals and other, but just that data that would indicate a failure of equipment. And we'll look at it in a Pareto chart type of an analysis. So if you look at this, the yellow bars are different circuits. And as you can see, the first 4 yellow bars represent something like 40% of the customer minutes of interruption for this utility. And as you go out, you get less and less benefit in CMI reduction, if that's your goal, as you get better and better circuit performance. So by attacking just those worst circuits for deteriorated equipment impacts, we now know where to go on a system. And typically, that's more like 10% of the entire grid. So let me show you an example of one of our customers who did a 3-year program with us and what they had, what their results were. And these were examples. This came from the the superintendent's presentation to his management team about some of the work that they did. So these four different circuits, one had an 84% improvement after the deteriorated equipment was removed. 64 miles had a 98% improvement after the deteriorated equipment was removed. 81 miles, and so on. Each of these were dramatic hits and improvements, both to him for the overall performance of the grid, but to customer satisfaction, worker safety, and costs. And he was so pleased with this, he continued it on then for many years, and is still working with us. Here's some more feeders, same type of analysis. But the key thing here is that the circuits were underperforming, but they weren't burning down. They were having flashover problems, which caused outages. They were having small issues that added up to many hundreds of thousands of customer minutes of interruption. And this is their overview of their trending for all their circuits. And he has now a goal of continuing that trend down as they do this feeder attack profile. He's not doing his whole system. He's doing those feeders that now move into the higher area of CMI contribution from electrical equipment. And we'll do that with you too. So this is a no charge service that we provide to give you insight into what you can accomplish and what you can gather. The key thing though is his customers avoided 2 million minutes of interruption in the past 2 years of this study. So IEEE defines partial discharge, the thing we measure, as 4 different types. The first is internal PD, and that's basically manufacturing problems or problems that have come from wear and tear. The next is surface PD, where contamination has gotten on the outside of insulators or any device, bushings, lightning arresters, combo units, all the equipment that has insulating properties that are exposed. And the beauty of this particular one, surface PD, is that it's a great participant in pole fires. So if you have pole fires, chances are it's surface PD, not always, but chances are that is causing the problem. And it could be something as simple as a $7 pin insulator that has dry band arcing going on. We can find it using the surface PD signatures. Corona PD, like I said, doesn't really apply much to distribution, but where it does, it's not a really good indicator of deteriorated equipment that's an incipient failure. Because in high humidity or light rain, dew, moisture, you're going to get PD from Corona on anything that is in the right voltage level, which I believe is above 37 kV, where Corona exists. That problem is, it just tells us we can't use that as an indicator of incipient fault. It may not be what you want. It may cause TDI and RFI problems, but it's not an incipient fault problem. And then the final one is floating components, where something has become disconnected. We found one lightning arrestor where the top wire had broken free and was just laying on top of the lightning arrestor. And that was wiping out all the communications in a broadband over power line system in a medium-sized city in Ohio. So, things like that are really important for a number of reasons other than just the equipment itself. This is an interesting report that evaluates how insulators are the biggest concern when it comes to transient flashovers. So a transient flashover is lightning striking your lines, a switching event, a recloser operation. Those operations cause high voltage spikes, transients on the grid, up to 2 times the normal voltage for a switching transient. and even higher for lightning. And if that one pin insulator is contaminated and is emitting these RF signals and the signature is correct, and you leave it in, that's where you're going to have a flashover. That's where you're going to cause the circuit outage based upon maybe your work, your transient switching transients on your system. That's why even these $7 pin insulators got to get out of the system if they're contaminated and could be an incipient fault. It's a process called scintillation, and I'm just going to walk through it very quickly here. But typically, there's always a capacitive leakage current from every device to ground, even the wires to ground. And that's just because of the dynamics of the AC electrical system. But when the scintillation shortens is a result of shortening the conductive path, or the non-conductive path, I'm sorry, of the insulator itself. So now you have a high resistive leakage current. That high resistive leakage current is going to find its way to ground through your wood poles. Based upon the pole condition, you're setting yourself up for a pole fire, which could go from a $10 replacement, maybe a $500 effort in the field to spin off and respin on a pin insulator, versus a $35,000 job to replace a pole or two. So it's important to get those out. And the issue is the scintillation comes from what's called a dry band arc. And that's a spot on the insulator that's been contaminated, gotten moist from dew, rain, snow, ice. A high axial current flows in that area on the surface, steams off the moisture, and bakes on that contaminant. And now you have something you can't wash off anymore, and it's going to present itself as an RF emission with the signature of an incipient failure. So like I said, normally they're low leakage currents that are capacitive, well within the system's capability to manage. But when they get into these problems of the insulator basically getting smaller because of these dry bands, you get into the situation of high resistive currents that can start a pole fire. And this just explains just a little bit more about the dry band itself. A lot of research on that. Love to have a presentation with you on that. If you have any questions, you can get a hold of me at any time. So how do you mitigate pole fires? Well, you have to find out where they are, and you have history of that. And in one example that we had recently, a wonderful case study for an engineer where we had 10 years of previous data. 10 years, this 200 miles of circuit in a Western utility city, major city, had 10 to 12 pole fires every year. Every year they spent $25,000 to $30,000 replacing these 10 to 12 poles with a new pole and new equipment. They brought us in because they had given up trying to eliminate these pole fires. They used IR, visual, all sorts of scanning equipment. They brought us in. In 3 weeks, we identified 65 components on this 200 miles. They replaced those 65 components, and for 3 years had 0 pole fires during those 3. So they went from a consistent 10 to 12 per year for 10 years to 0 the next year, and the 2 years following that, and that's as far as we've gotten so far. This is what we look at when we talk to a utility, because you're in regions across the country and they're different. How equipment fails, what equipment fails, the incipient failure modes across the country are all different. And we've divided the country up into 6 regions. So if you tell me what state you're in, I can tell you what we're going to find on a program pretty much very accurately. And if it doesn't match our projections, there's probably something else involved. We've worked with utilities that have lightning arresters that are failing at a much higher rate than we expect. It turns out the lineman needed training on how to install them properly. They were using their hydraulic tools, and they were breaking the connection inside the lightning arrestor to the MOVs. So just little things like that we can pick out and tell you how we think your problem has generated itself and how best to approach it. Maybe training, maybe replacement of equipment that was mismanufactured, whatever it is, we can start right there with you and give you a good view of your entire system and then narrow it down to those circuits that really require attention to address equipment related outages. So this is a tool we have that we're happy to run with you. It takes minutes to evaluate your system and tell you what you'll get out of a predictive maintenance program and how much it will cost you and what the ROI is for you at the end of the day. Because you do have to do something, right? If we tell you there's incipient failing equipment in your system and you don't replace it, what's going to happen? Outages. But if you replace it, you will avoid the outages that are associated with that deteriorated equipment. So we asked just a few questions: overhead mile length, what's your average repair cost, how many circuits do you have, a few things like that, your CMI, your safety, your SAIDI. And just with that little bit of data, we can do this. We can come up with an attack profile for your company that may be 10 or 15%. In this case, I took 50, everybody always says, well, you picked a great utility to show us here. Well, what I did was I picked 50 utilities in the Midwest, aggregated all their data as if they were one large utility. So now there's no sleight of hand here. This is real data, and this is data over a wide area of the Midwest. So 10% of this wide area would be about 1,500 miles, just 10%. So it'd be a huge utility. And we have estimates for what we can accomplish with a utility of this size in this region. And we looked at it from 10% of their grid being evaluated or 15%. And then we measured their equipment related CMI, which was in the 12 to 15 million minutes per year. And we estimated our impact on that. We can't fix everything with our system, but we can have a big impact, a big dent in the impact we have on the utility. So we thought we could drop their CMI by about 4 million minutes a year, either way. So what's the cost of that? Well, there's a cost for us to do our work. There's a cost for the utility to repair based upon what we find. And there's a total, so that gives you a total project cost of those two elements: repair, diagnosis, and repair. With that, we were able to reduce their equipment related SAIDI by 6 minutes to 7 minutes. And that's a big reduction because that turns into 2 to over 2 minutes of total SAIDI for their entire company, for this entire company. Typically, our customers tell us a CMI minute is worth something between 50 cents and $1.25. A SAIDI minute, though, may be $500,000 to $2 million of value. So these are real numbers that have a real impact on the performance, the cost performance of the utility. And as a result of that, in a 10% profile, this utility, this SimCity utility, would have an ROI of the project of over 400%. And if it dropped down to the 15%, which costs more, and because now we're doing more circuits that are less productive of CMI, you get a small reduction in ROI percentage, but it's still over 100%. So it means immediate payback. So these are really good projects, and this can be done before any PO is written or any quotation is written. You just call us, we'll run these numbers for you, and then you can make a decision whether or not predictive maintenance would be a good thing for your company. Now remember, there are these direct benefits that we talked about earlier: 38% reduction in injuries and fatalities, 33% reduction in overtime, and 18% reduction in the time to restore outages for the utility. But there's also these indirect benefits that shouldn't be overlooked. Higher customer satisfaction, reduce cost of outages because you know what you're doing now, and avoided regulatory penalties. So in summary, these are the benefits of the program. Helps prevent outages, particularly unexpected outages. It improves your indices if you measure those, SAIFI, SAIDI, and CAIDI. It reduces the risk of reportable OSHA incidents, which is not only important for that, but for the people who are reported on those events. You don't want your people being hurt at work. Improves customer satisfaction. It uses advanced analytics to make your work impactful to avoid equipment deterioration within your company. And it allows you to replace equipment that's going to fail soon before it fails and avoid the service interruption. So there are my contact information is under my name on that QR code. You can scan it right off your screen. There are a few other interesting papers that you can get, brochures and such that discuss specific issues. And I'd love to talk to each of you in more detail. And I'd be happy to run, as participants of this seminar, the complete financial analysis at no cost to you, just a request for some information from your team. And thank you very much. And I'd be very happy to take any questions at this time.
Thank you, John. That was an excellent presentation. Yes, we do have a couple of questions that come in. What resource commitment is there at the utility? It sounds like there's a lot to do.
Well, it sounds like it does, but there's really very little to do. So if you remember that utility with where we did 1,500 miles or so of work, they would have to repair on those circuits the equipment that we found. Now, typically in an urban setting, we find one problem every 4 miles. So that's one insulator, as an example, every 4 miles, not one pole, one insulator, and or one issue that requires attention. In a suburban area, it's usually more like one problem every 7 to 8 miles, and then in a rural area, it's more like one problem every 10 to 12 miles. So that's the work that the utility has to do that they wouldn't have had to do before. All the other work, the deployment of sensors, the analysis of the data, the collection of the data, and the presentation of the data back to you as a GIS file or as a report, whichever way you wish it, is done by Exactor as part of our participation in this program. So really, you've got some fair weather grid maintenance to accomplish to reap the benefits of what you would have happen with the outages, the unexpected outages.
Okay. What's the typical timeline for a project?
Well, that's a good question. It depends on some of the parameters of the project, but very typically, once a PO is written, in 2 weeks we deploy. In 4 more weeks, we're done with all of our data collection. So that's 6 weeks. And then another week or two, so let's say 2 weeks, for all of our analysis and reporting to be done. So we've got about 8 weeks from start to finish. And then it goes to the utility, and the utility needs to do the repairs to the grid. Let's say that takes 2 months or something. So the whole thing could be wrapped up in 4 months, and you'll have a different grid performing much better.
Right. Speaking of grids, if you have less than 200 miles of overhead, is there a viable option for utility of that size?
You bet. Yeah. Now we do have deployment costs, so it doesn't go down to zero for us to do something. But we have many customers in that size range. Our smallest customer has 500 meters, 500 accounts
Mm.
in their whole utility. One of them is a chicken farm, and that chicken farm has told the city that if they have a power outage of an hour, they'll lose 1 million chickens,
Oh
and
yeah.
they'll also move their chicken farm somewhere else. So it's very important to this very small utility to have their whole city funded basically by this one enterprise, and they don't want an outage. So we're an active part of theirs. So what we do for very small projects is we have a base cost that just sets a baseline cost for a project, which is usually very affordable. And then again, we'll do all the work, including that business analysis, so you can see what it would cost and what the ROI would be for you. It might be a little bit lower for a very small utility than a very large utility, but it's always more than 100%.
Okay. I know that wildfires have been in the news a lot lately, and this question concerns wildfires. Do you have any case studies that focus on wildfire mitigation?
Yeah, well, I mentioned the 200 miles, and that was
Mhm.
interesting because it was at a place where there was a very large airport, and that 200 miles was like right at the end of the runway. So obviously, it was contamination from aerial flights that were going over,
Yeah.
and that was a tremendous win for that utility. From a 10 to 12 coal fires a year to zero in immediately. Just for fixing 65 potential problems on 200 miles of grid. So 200 miles of grid would be what, 8,000 poles? So maybe 40,000 devices. 65 of them were identified as problems and solved the problem. But yes, we do pole fire mitigation programs across the country, particularly in the western half of the country, but across the country.
Right. Okay. I think you've probably covered this, but can I get an overview of potential costs and financial benefits before committing to a project?
Yes. So I'm going to just scroll back to that. This business case engine that we have literally requires 20 minutes of your time for us to gather the information we need, and we'll give you this complete analysis, both for a number of cases where we come up with that are valid for you. This was 10 and 15% of their that would give them these big ROIs and big wins. But this is a Sim City type of utility. Your utility is going to be different. Your safety are going to be different. Your costs of an outage, avoiding an outage versus responding to an outage are going to be different. So we just need to sit down with you. It's a 20-minute discussion. We'll give you a complete analysis, and you can look at that then and say, this makes sense to me. I'm going to put this in my budget. Or it's just not right for me. I'll continue the way I'm working.
Right. Well, that's all the questions we have for today, John. I want to thank you again for taking time to share this information with us. And it's been very, very informative, and I really appreciate that. Hometown Connections is proud to have Exactor as one of our very trusted partners, and look forward to having you folks contact John and find out how you can improve your utility just maintenance program. And I really am impressed with being able to go out and make these repairs in a nice sunny day instead of in a reactive situation where customers are breathing down your throat wanting to get the power back on during a storm. So getting it done while things are calm and collected and cool, and you can do it right and do it safely. So thanks again for everyone for joining in. And John, thank you again for your time and effort.
Thank you, Mike, and thank you to everyone who joined us. I look forward to talking to you. And if you have any trouble getting a hold of me, get a hold of Mike.
There you go. All right. Thanks, John. Have a good day.
The preceding presentation was a production of Hometown Connections. Thank you for watching, and be sure to like and subscribe.